Okay, lecture B for Intro to Chem Unit is about sig figs and scientific notation. So significant figures, I tend to shorthand that as sig figs. If you hear me say sig figs, that's what I'm talking about. Remember last lecture I said in math class you use fractions because math is using imaginary numbers, it's using the theoretical numbers, and it has to be very, very accurate. In science, we're talking about measurements, so the measurements that we're taking, and our numbers can only be as accurate as the instrument. So if you look at this example graduated cylinder we have over here to the side, it's marked, here's 70, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's 80. So each one of these represents the ones place. Okay, so 70, 71, 72, 73, etc. The proper way to read a graduated cylinder is to get at eye level and read from the bottom of the meniscus. So pretend I drew a straight line there. And then you're going to try to be as accurate as you can. Now I know for sure that 71, 2, 3, 4, 5, and so that's 76, that my measurement is somewhere between 75 and 76. Okay, so I know that for sure. So it's going to be 75 point something. The something isn't marked on here. I'm going to have to estimate that. So if I were guessing, I would estimate that at about 0.6. So I would read this as 75.6. The rules for sig figs is to use all of the actual places that are measured plus one decimal place that's estimated. So if the ones place is measured, you estimate the tenths. If we look at the two rulers, this first ruler is marked in ones. So 16, 17, and my measurement is somewhere in between. So I'm going to estimate to the tenths place on this ruler. So 16.2. So the 16, the ones place are marked. I'm estimating the tenths. On this ruler, the tenths place are marked. That's 16.1, 16.2, 16.3, 16.4, 16.5. So since the tenths places are marked, and so that's definitely 16.2 something, I actually want to erase that line because that's actually marked there. 16.2, I need to estimate the hundredths. In this case, I'm going to estimate the hundredth. This ruler is more accurate. Ruler B is more accurate because it measures more actual decimal places, and I would estimate that at about 0.5. So about 16.25. So everything that's measured plus one extra. Let's take a look at some other examples. Here I have a balance, triple beam balance. When you read a triple beam balance, you're going to be looking at the bars that are on here. So here's the hundredths place, right? So we know it's at least 300. Here's the tenths place, so we know it's at least 350. Here's the ones place. I know it's at least 54. They've marked the tenths place, so that longer bar is usually the 0.5, 0.6. And I estimate one more. Now if I'm looking at this and I think it's exactly on the 0.6, then I have to estimate that my hundredths place is 0. So a triple beam balance that measures, that shows you the tenths, it shows the tenths, you're going to read it to the hundredth. It shows to the tenth, you're going to read to the hundredth. Here's a burette. Now burettes are a little weird because they read backwards. So instead of a graduated cylinder where the 39 would be at the bottom and the 40 would be at the top, we're going to use a burette to measure how much we've added to something, so we read it backwards. When it's full, it's actually at 0. So this number is going to be 39, and they have the tenths measured. So if it's 39 point and the tenths are measured, so I think that is just a little smidge over 0.3, and then I'm going to estimate the hundredths, and I think it's just a little bit over, so it's either going to be 0.1 or 0.2. I'm going to say 0.2. Okay, everything that's marked plus one extra place. Okay? And again, some of the Regents questions that they might ask you how many decimal places do you read ruler A to? Well, if ruler A is marked to the tenths, you're going to read that to the hundredths. Ruler B, if it's marked to the whole numbers, you're going to read it to the tenths place. Okay, now that you know how to read an instrument to the correct number of significant figures, you need to know when you look at a measurement in a book, on a test question, how many significant figures there are. When you can't see the instrument itself, somebody's just reported significant figures to you, how do you know how many significant figures there are in that number? So we have a few rules, and they're not that hard. First, we have to know what counting numbers are. So 1 through 9 are your counting numbers. They represent actual things. Those are always significant. If you see a counting number in a number, the counting number always counts. So one of the things I'm going to tell you to do is when you see a counting number, make a little mark. 2 is a counting number, 3 is a counting number, that's it. There's nothing else left. This number has 2 significant figures in it. Okay? Now that leaves just zeros. We have a base 10 number system. The 0 is a placeholder generally. It's when there's nothing there to count, but you need to know that it's 10 and not 1, or 100 and not 10. We use zeros. If your number ends in zeros and there's a decimal in the number at all, that number is going to count. So if we look here, our first rule was counting numbers. So the 2 and the 3 count. Does my number end in 0? Yes. Is there a decimal in that number? Yes. So if it ends in 0 and there's a decimal, that one counts too. So this number contains 3 significant figures. Compare that to 20. 2 is a counting number, he counts. Does it end in 0? Yes. Is there a decimal here? No. So this one doesn't count. 20 only contains 1 significant figure. You may remember sometimes in biology, a measurement might have been listed as 10 or 10 point, and you want to know what's the big deal, why the decimal. In math class, you probably wouldn't bother with this decimal. Sometimes you saw 10.0. And again, in math class, you wouldn't bother with this extra 0 at the end. But when these are measurements, remember the 1 is a counting number, he counts. Does it end in 0? Yes. Is there a decimal here? No. So this number contains 1 significant figure. The 1 counts, he's a counting number. Does it end in 0? Yes. Is there a decimal? Yes. This guy counts. 10.0 contains 2 significant figures. So what this means is this instrument was marked to the tens place and they've estimated the ones. This instrument was marked to, or actually, so what this means is that this instrument was marked to the hundredths place and they've estimated the tens. This instrument would have been marked to the tens place, tens, T-E-N-S, and estimated the ones. Okay? That just leaves us with this 0 right here. So if this guy's got a counting number, he counts. Does it end in 0? Yes. Is there a decimal? Yes. So he counts. Now what do I do with this 0 here in the middle? Well, our rules say that any 0 that falls between things we've already marked as significant also count. So now this 0 becomes significant. And this instrument has 3 significant figures in the measurement. It was marked to the ones place. We've estimated the tenths. So that's the difference when you see 10 or 10 point or 10.0. It's how accurate the instrument was that took the measurements. Let's look at the rest of our examples down here. So if I look at a number like this, I go through the rules. All of the counting numbers count. So the 3, the 4, the 5, and the 9. Does it end in 0? Yes. Is there a decimal? No. So those zeros, that 0 doesn't count. Do either of these zeros fall in between things we've marked? No, so they don't count. This number has 4 significant figures. This one down here, counting numbers. 3, 4. Does it end in 0? No, so we ignore the second rule. Do any of these fall in between things that I've marked? No, so this number only has 2 significant figures. All right, now when it comes to scientific notation, again, we're going to do a number times 10 to some exponent. This number always has to fall between 1.0 and 9.9. So you have to move the decimal point in between, and this number also has to contain all of the significant figures. So if I were to write 23 in scientific notation, I would write 2.3 times 10 to the first. If I were to write 23.0, I would have to write 2.30 times 10 to the first. Because it has three significant figures, you have to show all three of those significant figures in the n. Okay. If I skip down here and I do that 345,900, I have to include all of the significant figures, the 3, the 4, the 5, the 9, but I get rid of the insignificant zeros, and I'm going to multiply that by 10 to the, that's 1, 2, 3, 4, 5. 1 times 10 to the fifth. 0.0034, the 3 and the 4. Remember, these zeros are not significant, so I'm going to get rid of them. Times 10 to, in this case, I'm going to use a negative exponent. Negative 1, 2, 3. So that's 3.4 times 10 to the negative third. Scientific notation, usually you guys have down because of math class, so I'm not too worried about it. If you're having issues with scientific notation, let me know and I'll go over the rules with you again. We will practice lots and lots of sig figs. You can give me examples and I'll go through and tell you how many sig figs are in each number. So we've looked at instruments with sig figs, we've counted sig figs. Now it's time to talk about what we do when we calculate with sig figs. So in calculations, you're going to have different rules depending on which math function you're doing. If we are adding and subtracting, we don't worry about significant figures, we worry about decimal places. So addition and subtraction, we're worried about how many decimal places our numbers have. So this should be pretty simple and straightforward. 21.023, 3 decimal places. 12.2, 1 decimal place. My answer can only have 1 decimal place. So if I pull out my calculator and I type the numbers in just the way they are, 21.023 plus 12.2, and I get 33. What do we got? 223. My answer can only have 1 decimal place, so I'm going to have to round that off. 33.2. Remember your rounding numbers. If the number after it is less than 5, you leave the number alone. If it's 5 or greater, you're going to round this number up. Okay, same thing goes for subtraction. 1 decimal place, 4 decimal places, 3 decimal places. My answer can only have 1 decimal place. So 719.0 minus 2.0004 equals minus 3.224 equals, okay, 713.7756. I can only have 1 decimal place. Here's the 7. The next number is a 7, so I'm going to have to round that up. So my answer is going to be 713.8. That's normally not a problem as long as people remember they are adding and subtracting. Multiplying and dividing, because of the nature of multiplication and division, you can all of a sudden end up with a huge number of decimal places. Remember, 1 divided by 3 gives you an infinite number of decimal places. So where do you round that to? This one has 0 decimal places. This one has 0. You can't round this answer to 0 decimal places. We need a different rule. So our rule for multiplication and division is to the round to the least number of sig figs. So this number has 1, 2, 3, 4, 5, 6, 7 sig figs. This one only has, here's my counting number. Does it end in 0? Yes. Is there a decimal? Yes. So that guy counts. Do these zeros fall in between anything I've marked? No. Do these zeros fall in between what I've marked? Yes. So those two count. So this guy has 4. This one has 7 sig figs. This one has 4. My answer is going to have 4 significant figures. So if I clear this out, 222.7234 times 0.004, and you can include those last three zeros if you want to, equals, now I have to round my answer to 4 significant figures. 1, 2, 3, 4. So I have to round it right here. The number right after that, 8, is a 9, so that's going to have to round up. So it's going to be 0.8909. So my answer is going to be 0.8909, correct, rounded to the correct number of sig figs. Okay, 4.7, how many sig figs does it have? This is easy. They're both counting numbers, so it has 2. 1.23 has 3, so my answer has to have 2 significant figures. So clear that. 4.7, remember that backslash means divide, divided by 1.23. I get a large number of decimal places, but I can only keep 2 of them. So 3.8, the next number after the 8 is the 2, so I leave it. My answer, 3.8. The correct number of sig figs. Constants, when we're talking about conversions, have an infinite number of sig figs. So usually when we're doing conversions, you're going to go from meters to millimeters. You don't worry about how many sig figs there are. They're not going to ask you to do that calculation to the correct number of sig figs. Okay, so scientific notation, there's the format. I already talked about it above. The first number is your n. It has to be between 1.0 and 9.9. Your 10 to the x. Exponent, always a whole number, positive or negative. Negative exponent, your number is really smaller than what you see, and you move the decimal to the left. Positive integer, and the number is really larger than what you see, and you're going to be moving your exponent to the right. Doing sig figs in scientific notation, that number in the end should contain all of the sig figs, so they're really easy if you see something written in significant figure. So for example, we'll use a mole, 6.02 times 10 to the 23rd. That's a big number. All of those zeros that don't count, we just eliminate. Our number has 3 significant figures. We just ignore all of the zeros. Those are all your insignificant zeros. These are your sig figs, 1, 2, 3 of them. When we do scientific notation, if you're adding and subtracting, you have to convert the numbers so the exponents match. So for example, if I have 2 times 10 to the negative second plus 3 times 10 to the third, not the negative second, the second, 2 times 10 to the negative second plus 3 times 10 to the negative third, I either need to make this to the third or this one to the second. So if I convert this to the third, what I have is 0.2 times 10 to the third. Because 2 times 10 to the second is going to be 1, 2 places, 200. 0.2 times 10 to the third is going to be 1, 2, 3 places, 200. So these are actually the same number. Now that the exponents match, I can do 0.2 times 10 to the third plus 3 times 10 to the third. You just add up the numbers. 3 plus 0.2 is 3.2 times 10 to the third. Multiplication, you're going to multiply the numbers in the front and add the exponents. So if I were to do the same numbers, 2 times 10 to the second times 3 times 10 to the third, we're going to multiply the numbers. So 2 times 3 is 6, and then we add the exponents. 2 plus 3 is 5, so your answer would be 6 times 10 to the fifth. When we're dividing, you're going to subtract the exponents. So to subtract the denominator from the numerator, the bottom number from the top number. So if we have 2 times 10 to the second divided by 4 times 10 to the third, we divide the numbers. 2 divided by 4 is 0.5. We subtract the exponents. 2 minus 3 is 10 to the negative first. We're going to fix this into proper scientific notation. So this number, this decimal is going to have to get moved over. So that's going to be 5 times 10 to the negative second. Easiest thing to do with scientific notation is, again, learn to use the calculator. Learn to use that exponent button. 2 times 10 to the second divided by 4 times 10 to the third equals 0.05. That's the same thing as 0.5 times 10 to the negative first. It's the same thing as 5 times 10 to the negative second, 2 places over. Learn to use the calculator, and you don't have to worry about the scientific notation math rules. All right, that's it for Lecture B.